A particle starts from rest and accelerates, as shown in this figure. The particle speed at 10 seconds and at 20 seconds. And so this is going to be the graph that we're looking at. So this is going to be the acceleration graph. And this equation right here, between the intervals of 0 and 10 seconds, you're going to have the velocity is going to be equal to 2 meters per second square times the time. So, and it wants us to determine the particle speed at 10 seconds. So at 10 seconds, you can see that the area underneath the curve is 20 meters, or you could simply just put 10 seconds, let t equals 10 seconds, and then either way, the velocity or the speed, in this case, is 20 meters per second. So let me rewrite that. So 20 meters per second. So part B is going to ask for the distance traveled in the first, it's actually asking for also in 20 seconds. So at this point, the acceleration is 0. But for a 5-second interval, so I'm just going to solve it here. From 15 to 20 seconds, I guess it would look like this. It would look like a new equation here. That would be -3 meters per second square times the time in between after 15 seconds. Initially starting at 20 meters per second. So this is going to be the new equation that we just set up here, and I'm not even pausing this video. So this implies between 0 and 10 seconds. This applies when t equals 20 seconds. And you can see that the math checks itself. So in between 5 seconds, the change would be -15 meters per second added to 20. So the other speed is going to be at 5 meters per second. That's what they're asking, folks. And the distance traveled in the first 20 seconds. All right, so this problem is a little more involved. I was going to do the kinematic equation formula, but what I'm going to do is I'm going to graph the t-axis and the velocity axis. And the reason why I'm doing this, folks, is because this makes it easier for me to solve the problem. Because I don't want to have to go through this whole drawing the kinetic motion from 20. In fact, that's how I solved it initially. But on this video, I'm going to do this a little different from how I usually solve this. But I'm going to just mark the equation between, I'm just going to mark the graph. So I'm going to mark this equation right here, 2 meters per second square, over the course of 20, so this would be 20 meters per second, over the course of 10 seconds. And then in the brief moment, the acceleration, the velocity is constant between 10 seconds and 15 seconds. So that means that this is going to be a straight line. So that's going to be 15 seconds. And then from 15 seconds to 20 seconds, you can see that the velocity is negative. I don't know if it's going to go further, though. I guess I'm not sure if it's going to go reach 0 at some point, but it did set 20 seconds, and that landed up to 5 meters per second. So I guess it doesn't. So I guess it drops down to that, and so that's 20 seconds. And you can see, folks, that all I did is really just mark the velocity versus time graph based on this information alone. And then you can mark the position versus time, but we know that the area underneath the velocity over the course of tiny delta t's is going to mark the actual answer that we're looking for. So you guys can pause this video and look at this graph, redraw it, and once you put all that pieces together, folks, you should have the position is going to be 262.5 meters, presuming that you start the initial position at 0. as traditionally if it doesn't specify. So that's the distance it travels. And that's all, folks. I hope you enjoy, and let me know what you guys think, and help this channel grow. All right, goodbye. See you.